Good morning to all, and I am Dr. R.S. Ramkumar, Head and Assistant Professor of Department of Mathematics at Sri Saranam College, Satur. Today we are going to see about the connected sets in a metric space in the subject set theory and metric spaces. Definition of a connected set in a metric space. First, you consider a metric space M with metric row. So in that metric space, let A be a subset of A be a subset. A is said to be connected if either of the following properties hold. The first one is, it is impossible to find non-empty subsets A1, A2 of the metric space M such that A can be obtained by taking the union of A1 and A2, and also the closure of A1 intersection A2 is an empty set, and also the A1 intersection the closure of A2 is also empty. So the next condition is when A comma row is itself recorded as a metric space, then there is no set except A and pi which is both open and closed in A comma row. So other than A, we cannot find the set which is both open and closed in A comma row. So if either of the condition holds, the given set A is said to be connected. So from that definition we can deduce the following results. The first theorem is the subset A of R with absolute metric is connected if and only if whenever A in A, B in A with the A is strictly less than B, then C belongs to A for any C such that A is strictly less than C which is strictly less than B. That is, whenever A belongs to A, B belongs to A is less than B, then the open interval A comma B is a subset of A. That means, so if we choose any subset A in R with the absolute metric, then this set A is an interval. So this theorem explains what kind of connected set in R with the usual metrics and what are all the forms of the connected set in R with the usual metric. So if the subset A is of R1 is connected, then A must be an interval. The next theorem, that f be a continuous function from a metric space M1 into a metric space M2. If M1 is connected, that is the domain of f is connected, then the range of f is also connected. F of M1 is also connected. Proof is very simple. Let capital A is equal to f of M1, the range of M1 under f, and so that f from M1 to A must be onto. Now I restrict the codomain to the range, therefore the function can be changed into the onto function. Suppose A is not connected, this one is a contradiction method, then there exists a non-empty proper subset B of A such that B is both open and closed in A. So we have already seen that the set is connected, then the only set both open and closed set is the A itself only. But here we assume A is not connected, so there exists a proper subset B of capital A such that B is both open and closed in A. But F inverse of B is also a non-empty proper subset of M1 which is both open and closed in M1. Because of the function is continuous, the inverse image of open set is open and the inverse image of closed set is closed. Therefore, F inverse of B is a non-empty proper subset of M1 which is both open and closed in capital M1. So which is a contradiction to our hypothesis because we assume that M1 is connected, so which is a contradiction. Therefore, A must be a connected subset. So next corollary, if f is a continuous real valued function on the closed and bounded interval. So now the domain is the closed and bounded interval and the codomain is the set of all real numbers, then that function f takes on every value between f of a and f of b. The image must be lies between the values f of a and f of b. Next theorem, let M be a metric space, then M is connected if and only if every continuous characteristic function on capital M is constant. This one is a necessary and sufficient condition for the metric space is connected. That is, if M is connected if and only if the function is identically 0 and the function identically 1 are the only characteristic function on M that are continuous on M. So, the function must be a constant function. So, whether it is identically equal to 0 or the identically equal to 1. We do not have the both images 0 and 1 if M is connected. Next one is a definition of a bounded set. Consider a metric space M with a metric rho. So, yes, the subset capital A of M is said to be bounded if there exists a positive real number capital L such that the distance between any two points under rho is less than or equal to L. So, if you choose any point x comma y belongs to a arbitrary points, and you measure the distance rho of x comma y. So, that distance is always less than or equal to L. So, for any 2 points it should satisfy the condition rho of x comma y is less than or equal to L, then the given subset A of M is said to be bounded. So, if A is bounded, we can define the diameter of the given set A, shortly diam of A, that is defined as the least upper bound of the distances of x comma y. So, x and y belongs to A. Just to measure all the distances between any 2 points and then take the least upper bound, we get the diameter of A. So, if A is not bounded, then the diameter of A is equal to infinity. This one is an example. The interval open interval 0 comma infinity is not a bounded subset of R1 because you cannot find L such that rho of x comma y is less than or equal to L for any x and y belongs to the open interval 0 comma infinity. However, 0 comma infinity is a bounded subset of R with discrete metric because of the distance between any 2 points in a discrete matrix is always less than or equal to 1, whether it is 0 or 1. If you consider the distance between the same points rho of x comma x, that must be 0, and the distance between x and y where x and y are distinct, then the distance is 1. Therefore, the L value is 1. So, it satisfies the definition of the bounded set. So, open interval 0 comma infinity is a bounded subset of R with discrete metric. Indeed, the diameter of any subset capital A of R with discrete metric is equal to 1. The maximum distance is 1 in the R with the discrete matrix. Therefore, the diameter value of any subset is always 1. Totally bounded subset, let M comma rho be a metric space. The subset A of M is said to be totally bounded if a given epsilon greater than 0, there exists a finite number of subsets A1, A2, etc. An of capital M such that the diameter of each subset AK is always less than epsilon for every k is equal to 1 to n, and such that the given set A is contained in the union of the all AKs. So, A1 union, A2 union, etc. An. So, this one is a definition for the totally bounded set. So, for any epsilon, for any real number, positive real number epsilon, we can find a finite number of subsets A1, A2, An of a given metric space M, and each set have the diameter is less than epsilon, and also the given set A is contained in the union of all the sets A1, A2, An. The next theorem is for any metric space M comma rho, the subset is totally, if the subset capital A is totally bounded, then A is also bounded. So totally bounded condition implies the bounded condition. Thank you.